everyone. My name is Eli Norris, a second-year PhD student in Material Science and Engineering at Texas A&M University. Today I'm going to do a brief literature review over an article titled Unsupervised Learning, the Aided Exploration for Accelerated Design of Superalloys. This paper was published by Liao et al. In MPJ Computational Materials this year in 2024. So the motivation for this paper is to, of course, design a new superalloy, but why? So superalloys are commonly used in the turbine blades in gas turbine engines. And it's argued that if we can increase the operating temperature of these blades by 100 degrees Celsius, we can increase the thrust produced by these engines by 20%. So there is high motivation to make the next generation of superalloys that can operate at higher temperatures, and they don't have to go that much higher. 100 C will do. And the unique thing about these alloys is that they get their properties, their high temperature strength and high temperature stability from this gamma prime phase in the material. But if we really want to push the operating temperature of these materials, we need to have gamma prime. We need to have this solvus temperature be higher. We need to make the gamma prime phase exist at higher temperatures. We have to push this phase field higher. And so one way we can try to design a new alloy that's going to have a higher gamma prime solvus temperature is through the use of machine learning. Because we know that gamma prime solvus temperature is pretty much predominantly dependent on the material chemistry. And we can use machine learning to predict what will be the gamma prime solvus temperature for a given chemistry if we set it up correctly. So there are two main methods that the authors said you could go down. You can do a pure prediction-oriented search, but where you have your data set, you do regression, and then you do interpolation. But this is often biased to only do interpolation due to limited data and a very large unexplored space. So you are not doing much extrapolating. In the author's framework, it is very much centered around extrapolation. You take the data set and you still use regression, but then you use unsupervised clustering, interpretation of the features, and similarity between alloy chemistries to do an extrapolation out into these vast unexplored chemistry spaces. So the approach that was done in this work is they start by acquiring the data from literature. From a literature survey, they found 179 data points on cobalt-based, cobalt-nickel-based, and nickel-based superalloys. And then they do what is called feature engineering, because in machine learning, the features are what identifies your material. And these can be things like enthalpy of mixing, atomic radius, etc., etc. And they do the feature engineering, and then they go on to define what is the chemistry space going to be. They initially defined a very fast chemistry space of about 89,000 alloys, and then they went and did some refining of this space, eliminating alloys that would immediately not be feasible, constraining it a little bit. And then they do unsupervised clustering. So they cluster the alloy compositions that are thought to have very high solvus temperatures. They cluster these materials based on the features that are going in to the prediction of that solvus temperature. And they're able to extract the cluster that has the largest effect on solvus temperature, because this gives you the features that are going to cause the most change to that temperature, and we can find the regions that will be targeted for improvement in it. And then they go and want to understand really how these features influence the gamma prime phase. And then we ensure that designed alloys are distinct and similar, because if they are not distinct from traditional alloys and you are just only slightly modifying the composition, then you are not exploring this vast space. And then they take these I thought to be ideal compositions, experimentally make them, and we look at the results. So kind of breaking this down into the parts, not all features contribute equally to a target property, and there is no universal machine learning algorithm suitable for all databases. So they have to do what is called feature engineering. So initially they generated 60 features, but this is very large. This data set is highly dimensional, and it can be very computationally expensive to work with. But to reduce this dimensionality, they used what is called a maximum information coefficient, and this can determine the nonlinear correlation between two features, as well as that feature and the target property. In doing this, they were able to reduce it from 60 to 22 features, and you can see the logic that they applied here. So they take two features, they calculate this maximum information coefficient, and they determine if it is above a value of 0.8, then we can retain the most important of the two features and we can eliminate the second one, because both are essentially telling us the same thing, but you don't need both. You only need one. And in the case that both features are not giving you a MIC value greater than 8, they are both kept, and then the process continues for another pair. And they keep doing this for all pairs of features. And they're able to reduce the dimensionality and only select what is important. And then you can plot a correlation heat map, and you can see exactly which features are the most important on the gamma prime Solvus temperature. So after doing this, they trained a gradient boosted tree with 4 of the most important features. And this is important because though this is a supervised machine learning model, it is important because we need a way to quickly query what will be the Solvus temperature for an arbitrary composition. Because now that this is trained on the 179 compositions, we can easily go and give it a new composition from the unexplored space, and it can tell us what will the Solvus temperature be, and then we can cluster them accordingly. So after doing feature engineering and training this surrogate model to predict the Solvus temperature, they needed to refine the search space because the search space was so large, about 89,000 alloys. And so to screen this and reduce the feasible design space, they train a classifier on chemistries that have gamma prime and chemistries that do not have gamma prime. And this classifier can classify the alloys in the unexplored search space as either having gamma prime or not having gamma prime. And if it's not having gamma prime, you can immediately eliminate that data point because it's not going to be useful for this study. And this is able to reduce the number of feasible or thought to be ideal compositions by half. So now getting into the unsupervised learning, they take the 4 most predominant features and they use these as inputs to a t-SNE algorithm. The t-SNE algorithm is a clustering algorithm that can take high dimensional data and it can find clusters and regions of clustering. And so what we can do is we cluster the materials, or we cluster the compositions based on similarity in their features. And those in the same cluster also have similar predicted gamma prime Solvus temperatures. And if you look at the clusters on the figure on the left, you can see that there are in fact distinct regions of clustering with regards to the similarity in the features. And we can see that if we look at this candidate region very far out on its own, it is this single region of dark blue points, which has the highest Solvus temperature. And these compositions are similar to each other, but yet different from the training data. The training data is marked by the orange triangles. So if we didn't do clustering, most likely we would only be able to interpolate around where these triangles are, and we wouldn't be able to extrapolate out into this unknown region. And with regards to similarity, it is important to know that are these predicted, this candidate region, how different are these alloys from those in the original training data set? And if we look at the figure on the right, we can see there is a difference value in the heat map. And basically what this shows is this is a similarity between the compositions. It's almost like a Euclidean distance between alloy compositions in a high dimensional space. And you can see that when you compare the original alloys to the candidate alloys in the bottom right, all of them have very high difference values, meaning these are in fact distinct compositions that are unique, and we have explored an unknown region, and we are not simply interpolating closely around each other. So big picture, what did they find? Using this technique, they were able to design 9 new alloys, and they were predicted the gamma prime solvus temperature and measured the gamma prime solvus temperature. And of the 9, the highest improvement they saw was 50 degrees C. And this is still good because that can improve your engine thrust by 10%, which when you're talking economics, that can be a lot. That can be a lot of fuel that can be saved, and money as well. But along with finding these new alloys with higher gamma prime solvus temperatures, they also uncovered a new trend because they looked very closely at how do these features influence this gamma prime solvus temperature. And what they found looking at this figure on the right is there is almost a linear trend between the negative enthalpy of mixing and the change in molecular volume. And you can almost see that there's a linear trend. As you start to maximize the negative enthalpy of mixing and change in the molecular volume, we are able to push that solvus temperature to higher temperatures and achieve exactly what they wanted to do. So the presented framework here, it is very effective in guiding the selection of target candidates from a large space. The key lies in that they are specifically integrating unsupervised clustering, local contribution analysis, and similarity evolution. By using these 3 things, they are able to further improve the predictive capability of traditional supervised learning methods. Because if you are just doing traditional supervised learning predictions, you need a very large and evenly distributed data set to have a robust exploration model. But this framework has only 179 data points that are not evenly spaced. But using unsupervised learning, we were able to achieve this new knowledge in the relationship between enthalpy of mixing, molecular volume, and gamma prime solvus temperature.